Hi, I'm Adam Sunderland. My colleague Adam Chalmers and I are building a CAD suite that streams from the cloud. It's called Zoo, and we're excited to talk to you about how we keep its latency low enough that it still feels like it's running locally. So, like I said, I'm Adam Sunderland. I work on infrastructure here at Zoo. Previously, I worked as a site reliability engineer at Zapier, where I helped scale their application to running many tasks for many users. I love telemetry, metrics, and graphs, and I love using them to understand the applications that I'm running. 3D printing and woodworking are my biggest hobbies, and it's really exciting that I get to work on a cloud application that kind of supports those hobbies. I'll hand it over to Adam to introduce himself.
Hi, I'm the other Adam at the zoo.dev, Adam Chalmers. I previously worked at Cloudflare for around 5 years, where I got to really appreciate writing really low latency services. And that came in useful when we're writing a remote CAD app for zoo.dev. I also blog about programming at adamchalmers.com. And at my work, besides keeping latency low, I'm also main developer on our backend APIs and for our language that we're building for 3D design. So what is zoo.dev? Well, we're making a CAD app that looks kind of like this. It's got a code editor on the left. It's got a GUI mouse-driven editor on the right with visuals. You can use a command palette that drops down. You can spin the view around and edit it either with code or with your mouse and keyboard. And this is all streaming the visuals from the cloud. So when you're rendering graphics in the cloud and you're streaming them down to the user, obviously you incur some latency. Our goal is to keep the latency so low that customers don't realize the CAD suite is running remotely. And so far, we're succeeding. But this has taken a lot of work to keep the latency that low. Why even bother? Why not just render the graphics locally so we wouldn't have to worry about any latency at all? Well, there's a lot of advantages to having a CAD app that runs in the cloud. For one, the user's laptop never has to do the rendering on device, so their fans aren't going to spin up. Their battery isn't going to drain. Their laptop isn't going to get so hot from all the power it's consuming that it burns their lap. This is quite a nice experience for the users. It also means that you don't have to buy a new laptop when a new kind of graphics card comes out you want to upgrade to. You'll just wake up one day and your CAD will feel faster because we've upgraded to faster GPUs in the cloud. Waking up and just seeing your software get faster from one day to the next is a pretty nice experience for users, I think. And if you're a CAD hobbyist who doesn't have a company to buy you a big, beefy gamer laptop with a massive CPU and GPU and big fan, that's okay, because you can use a low-power device as a hobbyist or a student or a new CAD person trying it out for the first time. And for us as developers, it's nice to be targeting the cloud instead of user devices, because we don't have to worry about supporting every combination of OS and CPU architecture and graphics stack and graphics hardware. We can just target Ubuntu on an x86 CPU with an Nvidia RTX GPU that we speak to via Vulkan. No need to worry about which kind of ARM CPUs are supported and whether it uses the Metal API or DirectX. Having one environment to target really simplifies deployment. And we're building this CAD app via an API, and we think that'll be really helpful for users. You won't have to build your own CAD app anymore if you have a really specific requirement. Like I met a guy at RustConf a few weeks ago who had to build his own Foundry, his own sheet metal Foundry CAD app to minimize the amount of phone calls he had to do to go back and forth with customers who kept sending him invalid CAD designs. He could just get his CAD app that was perfectly catered to his Foundry, and customers would be forced to design for the right kind of machines they could work with. He had to build this whole CAD app himself, which is kind of a pain. But if we'd been around, he would have just been able to build on our API, build an app that fit his requirements, and let our API do all the heavy lifting of graphics and computational geometry. Also, an API means it's really easy to integrate with other software. So if you want to have a CI system for CAD, or a file syncing system, or to make new CAD files programmatically in response to user events, we have an API that can tie that all together. So let's get into the latency.
Right. So how do we minimize latency? We've focused on two things. First, our infrastructure and the choices we make for how customers connect to us. Second, once we're connected, there are a lot of things that we can do to ensure that communication is efficient. So, onto our infrastructure and how we've designed that for low latency. Geographic latency is the most important thing when it comes to connecting customers to appropriate copies of our infra. We want streams to look fast and local, and to do that, we have to pay attention to how far data travels. We can't just run everything in Virginia. We had to use multiple regions early on, and we have 4 in production now, and we can easily scale to more as we need. This means that we have to pay attention to the hardware that we're using to stream our applications to users. CPU-only machines are easy to find and use. Code you write for most x86 processors will work on most others. GPU machines are harder to find and harder to use. Not all GPUs exist in all data centers, and not all GPUs have video encoding hardware, for example. Like an H100 just doesn't work for us because it doesn't have the video encoding hardware. We also can deploy to our own physical hardware. We just got a small proof of concept cluster running in our office in LA, which minimizes geographic latency about as much as we can for somebody who's working in our office. And hardware availability is less of a concern as we can just buy the exact hardware that we need. Soon, our plan is to expand the small cluster to serve as a 5th production region to minimize latency for our customers near Southern California. So we have to deploy to lots of regions and pay attention to the hardware we use. How do we actually connect customers to our geometry engine? Our geometry engine uses cloud GPUs to render models visually and stream that back to our users. It handles the command processing and ultimately translating those calls to the GPU. This requires that we carefully handle the statefulness of that rendering and encoding pipeline. Our CPU side API handles a lot of what you might expect of an API server, like auth, sessions, and other API calls that we handle. The engine manager it also relays WebSocket communication with the engine assignment it receives from our engine manager. The engine manager itself tracks active user sessions on the many available copies of our geometry engine and ensures that customers connect to the right one. Once we've connected a WebSocket from our customer to our API and finally to our engine, we can establish WebRTC connections for UDP data and video directly between the customer and our geometry engine. A benefit of this approach is that we can scale these workloads independently to save on cost. Our geometry engine is basically a video game engine that we're streaming to our customers. So we can lower our costs by minimizing the number of GPUs we're using and only scaling up based on active streams. On the CPU side, we can proxy multiple connections through the same API server, so we can further minimize resource usage doing that type of work. This decoupling of GPU and CPU is also useful for some future improvements we want to make. For example, we can use our CPU-only API to seamlessly connect to a new engine and replay the current state in the event that we want to deploy some new version of our code without impacting any customer's work while they're using the application. So now that customers are connected, let's dive into what happens during the streaming session.
So during a streaming session, we've already connected, we've got the user running on very fast hardware that's close to them. But as we all know, just because you're running fast hardware close to the user doesn't mean your app is actually fast, because you can still write very slow software. Doesn't matter how fast the hardware is. You can write some bad software that slows the whole thing down. So how do we keep the software fast when it actually runs? Well, firstly, we had to build a new CAD kernel from scratch. Most CAD apps use the same old kernels that have been used since the 80s, Parasolid and other things. And these CAD kernels are really well battle tested. They're huge libraries of code that exists to understand the boundaries of objects, the intersections of curves, where edges lie. They're very well battle tested. They've put people into space. And even more impressively, they've actually brought people back down from space. That's a lot harder. But because these kernels are fairly old, they're written for single-threaded CPUs. And all these speed advances in CPUs have come from adding more and more and more processors to new CPUs. So even though they work very well in single-threaded environments, they don't really work very well in multi-threaded. Now, they've been retrofitted to understand multi-threading, and some parts of them are multi-threaded, but as a lot of CAD users know, you eventually run into part of the app where you hit a bottleneck that's single-threaded. So we knew we had to write a new kernel that was built from the ground up to use multi-threading and the GPU as often as possible to get the most parallelism. But once we've done that, the main source of latency in our program is I/O. I mean, the front end can draw its UI very quickly. The back end can render graphics and run calculations very quickly. But I/O between the two of them, that'll always be where the latency is. So it's really important to transmit data very efficiently. We have a lot of different kinds of data, and we send them all differently. We open up WebRTC, and we're using WebRTC video for the video. But WebRTC actually has data channels too, not just media channels. Data channels can send structured data either as text or binary. And the nice thing about WebRTC data channels is you can configure how reliable they are. You can trade off reliability and latency as two concerns. You can choose the right compromise for your app. In our case, we dial the reliability down so that we can dial the responsiveness really up. So we get UDP-like semantics for our data channels. This is nice because we can minimize latency, but we do have to build reliability back up in the app layer itself. So the way we do this is for, say, the user moving a mouse. If you're moving the mouse from one end of the screen to the other, you're smoothly dragging it, we're going to send mouse events every 30 mouse events every second. If one of these mouse events gets dropped, that's okay. We don't want to hold up the rest of the mouse events to wait for that slow mouse event to come back, because there'll be another one in the next 30th of a second anyway. So we get nice UDP-like semantics. This means we have to send logical timestamps with every event, and the backend tracks the last timestamp it's seen. This way, if a stale event comes in later, we don't snap the view back to an old position that the user's already done with. We can ignore these stale events and not even process them. The next kind of data is reliable commands, things like updating the geometry, like adding a new face or extruding a circle upwards into a cylinder. It's really important that these events don't get missed, so they have to be sent over TCP and reliably transmitted. We use WebSockets to make sure that the user's front end is communicating with the exact same graphics backend, the same node, the entire time. Because this node is stateful and we don't want to have to rebuild the 3D graphics context. The next kind of data we transmit are files. When you import a CAD file to start off, or when you export your model after you're done with it, you get a CAD file being sent over the network. And these files can be pretty large, so it's important we encode them efficiently. This means no JSON, because binary does not encode efficiently in a text-only format like JSON. You don't want to have to base 64 something, because that'll add latency when you encode it, it'll add more bytes to be sent over the wire, and it'll add latency when you decode it. So not going to happen. So we use BSON, a binary JSON-like format, to send this data. We generally send everything else over text because everything else tends to be small and therefore it's easy to debug with JSON. But with these files, we know they're going to be really large, so BSON makes more sense. And of course, we send video data. We're streaming the UI of the CAD app, kind of like running a remote cloud gaming service, basically. And we use WebRTC media channels for this. But there's a lot more to keeping video low latency than just use WebRTC.
Right. One of the things we use to keep that low latency is called NVENC or NVENC or Nvidia Encoder, however you want to call it. It's physical hardware that is dedicated to encoding video data into a specific compressed video format like H.264 or AV1. Different NVIDIA GPUs have different NVENC capabilities, or they may lack the hardware entirely. Some GPUs may have multiple NVENC chips, with each one supporting multiple encoded videos. The actual capability of each chip depends on the resolution and codec being used by our customers. It's worth limiting ourselves to only the hardware with NVENC because it's very fast and drastically reduces the amount of data we have to copy from the GPU to the CPU. Because we can generate and compress the video data entirely on the GPU, we only need to send the encoded data back to the CPU each frame. Since it has dedicated hardware, it also has a minimal impact on the general GPU utilization. But this does add another dimension to scaling, as NVENC has its own capacity and utilization metrics that we have to pay attention to.
So the last remaining source of latency is going to be I/O between different parts of the system. There's three main places latency sneaks into a program: within the front end, between the front end and back end, and then within the back end. And in all these cases, latency comes from sending data from one place to another. I/O, classic. So the way we solve them in all these cases is to try and batch many small I/Os into fewer, larger I/Os. I'll give you some examples. Firstly, within the front end, the client, we use JavaScript to serve the UI, and Rust compiled into WASM to do the calculations, geometry, and manage our network connections. Now, Rust or WASM tends to be very fast because it compiles down to really efficient native code with a very, 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 very thin VM layer around it. But it's not magical performance data. It won't guarantee your app is fast just because you're using WASM. In order to keep this WASM performance fast, you have to avoid making too many round trips between the JavaScript side and the WASM side, because every time you do, you need to copy data into or out of the WASM VM. So you don't want to interleave JavaScript and WASM processing, having each side wait on the other one. That's going to really kill your performance. What you instead want to do is kind of let JavaScript drive the UI and let the WASM side drive some calculations. So we have the UI doing some UI logic, then it hands it off to Rust to send a bunch of API calls and render some calculations. And then when it completes, it sends the data back to the JavaScript side. Doing these batches of computation on each side is way more effective than trying to interleave data between the two of them and paying that WASM transmission cost all the time. So if you minimize the data you're sending, you'll get less latency. We actually really like using Rust even without the speed advantages of WASM, just because it lets us reuse the same libraries in so many places. We have a Rust library for our programming language KCL, which compiles down to being API calls to the CAD API. And means we can use it in all kinds of places. We can use it in our web app client. We can also compile it to a native code CLI so that your terminal power users can use it. We even packaged it up into Python so you can get the convenience of Python libraries, which is really helpful for a lot of programmers out there, but still get the performance of Rust. And we also run this library on our backend as well, so the backend knows it's using the same types that the front end is expecting. When it comes to sending data from the client to the server, all those round trips will also add latency. So again, we try to batch round trips. This means if you're drawing a triangle, don't send 3 separate lines, each with their own round trip. Send one round trip of data that encodes all 3 lines of the triangle. Basically, this means that our API can run in 2 modes. There's a single command mode where you send a request, you get a response, or there's a batch mode where you send a whole heap of commands, and then you get a big map showing for each command what was the response. Did it succeed? If so, what was its data? Did it fail? If so, what was the error? Or maybe it was cancelled because a previous command in the batch failed. Ideally, we'd batch the whole program into one big batch, but that's not possible because say you need to make a query to the engine, and then depending on the result of that query, you'll do something. Maybe you'll change which API call you make next. Well, you'll have to wait for that batch to terminate and check the answer before you can send the next batch. So as we're evolving our programming language and our coding environment, making better use of batching is going to be the key to keeping it fast and responsive. The other kind of latency comes in the backend itself. We want to minimize the amount of data being sent from the CPU to the GPU back and forth, and we want to make better effective use of the GPU, not repeat the same calculations over and over again. So luckily, this actually maps really nicely to CAD. Say you're drawing a gear with 14 sides. You don't want to draw all 14 teeth separately. No, a typical CAD programmer would draw one tooth and then click the pattern button in their UI and use that to radially replicate the gear teeth around the circumference of the gear 14 times. On our backend, we understand that this pattern can translate into GPU instancing. So on the GPU, we say reuse the previous results of this geometry calculation. Because both our front end and our back end understand this calculation should be repeated, we don't have to worry about redoing unnecessary work.
So, to recap, we have to be located close to our customers to minimize geographic latency. We also take advantage of the powerful GPUs that exist and the video encoding capabilities that they all have, or that some of them have. UDP means that our video and data channels are as low latency as possible. And finally, we combine operations to minimize the number of round trips between our customer and our servers.
Thanks so much for listening to our talk. All these ideas put together have meant we've been able to keep a CAD experience that still feels pretty local, even though you're actually running in the cloud. Hope you enjoy the rest of the conference. We're really excited to learn a whole bunch about latency and high performance while we're here. And feel free to connect with us online. We can the Zoo modeling app is currently free for everyone while it's in alpha and beta. So we'd love to get your feedback on it and any tips and tricks you want to share. All right, have a great rest of the conference.